This lesson covers graphing piecewise functions. As you'll recall from one of the lessons last week, a piecewise function is one that is defined by more than one equation. It could be simply two equations. It could be 3, 4, 5. As many equations is necessary for that particular situation. Now, most of the ones on this note sheet are defined with two equations, and I believe the last one is defined with 3. So remember, with your equations, when you're looking at your piecewise function, this top equation, 2x plus 3, is defined for any x value from 1 and smaller. This one, negative x plus 4, is defined for any x value bigger than 1. So what we're going to do first is we're going to make an xy table for each one of our equations over its defined domain. So the domain for the first equation has values less than or equal to 1. So I'm going to start at my boundary number of 1, and I'm going to work my way backwards for a significant number of points, usually 3 or 4. And all we're going to do is evaluate. If you plug in 1, you get a value of 5. 0 would give you 3, negative 1 would give you 1, and negative 2 would give you negative 1. And so what I've made is a list of ordered pairs, and all we're going to do is graph the ordered pairs and connect the dots. Now, when I make the table for my second graph, I'm going to make it in a different color. We're going to use values from 1 and smaller. Now, here's the deal. Even though 1 is not included in the domain, it's a boundary number. So we are going to plot that value of 1, and we're going to go up from there. And I'm going to do 2, 3, and 4. And again, 3 or 4 points is enough. Now, what we're going to do with that boundary number of 1 with this purple equation, we'll talk about once we get to the graph. But right now, let's just evaluate. So if I evaluate with 1, I get a value of 3. If you evaluate with 2, you get 2. Evaluate with 3, you get 1. Evaluate with 4, you get 0. So what are we going to do now once we've got our two tables of values? Well, we're going to graph the points. So let's start with our top equation. If I graph at 1, 5, I get my first dot, and then at 0, 3, and then at negative 1, 1, and at negative 2, negative 1. And so if you notice, this equation is represented by anything less than 1, which means that as I connect my dots, I'm going to continue past my last dot and show that my line keeps going. If I graph my purple dot, now let's pay attention to the fact that this first dot is technically not a part of the domain of the second graph. So when I graph that point, I'm actually going to graph it and show that it's not a part of the graph by putting an open circle. And then the rest of the points I'm going to graph like normal, 2, 2, 3, 1, 4, 0. And when I connect my dots, I'm going to continue on past those dots because that equation is defined for any value of x bigger than 1. So if you notice, since I put an open dot at 1, 3, my function still passes vertical line test, because if I put a vertical line through an x value of 1, I still only hit the graph one time because it hits the closed dot but passes through the open dot. That's why it's okay to graph that extra boundary point with both equations, so long as you put one of the equations with an open circle rather than both of them with a closed circle. If we go down to the next one, the next one is, again, two linear equations. So the first thing we're going to do is make a table of values. So for my top equation, I'm going to use purple. And I'm looking at values greater than or equal to negative 1. So I'm going to start at my boundary number and just go up. And all I'm doing is evaluating. You plug in negative 1, you get negative 2. You plug in 0, you get 3. Plug in 1, you get 8. Plug in 2, you get 13. In the next one, I'm going to use a color of blue. And again, even though negative 1 technically isn't part of the domain, I'm going to graph it as a boundary number. So I'm going to start at negative 1, and I'm going to go down from there. And so I'm going to move down to negative 4. And so again, what we're doing here is we are evaluating each one of these. So if I plug in negative 1, I get 9. Plug in negative 2, I get 13. Plug in negative 3, and I'm going to get 17. and plug in -4, and I'm going to get 21. So if you notice, this is going to go a little bit off the graph. So to kind of fix that, I'm just going to make sure that I go by 2s. So I'm actually going to do that just on the y-axis. So my x-axis, I'm going to count normal. My y-axis, I'm going to go up by 2s. So let's graph our first equation in the purple. -1, 2, -2, excuse me, should be down here. 0, 3 is going to be here. 1, 8, and then 2, 13. And this is for values bigger than -1. So as I connect my dots, I'm going to make sure and show that my graph continues to go beyond those to the right, not the left. If I graph my blue, again, remember your y-axis is going by 2s, so I would be -1 and then 2, 4, 6, 8. And when I graph my first dot, remember it's not technically included, therefore I'm going to put an open circle. -2, 13. -3, 17. And then the last one is at -4, 21. So I'm going to be a little bit off the graph. And again, this one is going to continue off to the left because this has x values smaller than -1. And so there's your your two equations, I should say. And again, notice because I put an open circle at -1 for the blue equation, this would still pass vertical line test. In the next problem, we switch it up a little bit and we start talking about a line and a quadratic. So my first equation is linear, and I'm looking at values that are smaller than -3 or equal to -3. So I'm going to start at -3 and I'm going to move down. And as I evaluate -3, I'd get -2. If you evaluate at -4, you'll get -5. If I evaluate -5, I'll get -8. And if I evaluate -6, I'll get -11. If I switch over to my quadratic, now keep in mind a quadratic is going to make your numbers get larger a lot faster. And I'm looking at values greater than -3. And again, we're going to use, -3 as a boundary number and then go up from there. And so as we graph, if I evaluate -3, -3 squared is 9, 4 times 9 is 36, and if you subtract 1, you get a y value of 35. -2 is going to give me a value of 15. -1 is going to give me a value of 3, and 0 is going to give me a value of -1. So let's start by graphing my linear equation first. If you notice, the purple goes up by quite a few, so I'm actually going to make my scale go by 5s so that I can fit the entire thing on the graph. So my blue equation, -3, -2. Oops, wouldn't be down that far. 1, 2, 3. And then we've got -4, -5. And then we've got -5, -8. And then we've got -6, -11. Something like that. And then as we connect our dots, we're going to move to the left and show that it goes beyond those points. When I graph my purple, again, remember your y-axis is going by 5s. So 1, 2, 3 to the left, and then 5, 10, 15, 20, 25, 30, 35. Now when I plot that point, remember it's an open circle. And then we're going to come down and we're going to do -2, 15. Then we're going to do -1, 3. 0, -1. Now if you notice, this continues to dip, and then the question becomes, well, when does it start to rebound? Because a quadratic is a parabola, so we know it's going to be a U-shape. Where does it rebound? So as you notice, it doesn't really show me with the coordinate points that I graphed, so that means that it's my responsibility to graph an extra point to find out where it rebounds. And I would continue graphing extra points until I find that rebound point. So if I plot 1, notice if you plug in 1, you're going to get a value of 3. So if I go over here and plot that, notice that my purple has gone down, gone down, gone down, and then now it's rebounded up. So I know that I plotted enough points, and as I graph, I know that it's going to come back up and look something like that. And again, notice that my equation would pass vertical line test because if I drew a vertical line through -3, it would technically only hit the graph once, hitting the blue closed dot and passing through the purple open dot. Last one has 3 equations. So in order to graph these, we're going to make 3 separate XY tables. So let's talk about the first one. This one is involving numbers bigger than 4. So we're going to start at 4 and go up 5, 6, 7. If you plot each one of these, if you plug in 4, square root of 4, or 1 minus 3 is 1, or 4 minus 3 is 1, square root of 1 is 1. Then you're going to get a value of square root of 2. Then you're going to get a value of square root of 3. Then you're going to get a value of 2 because it's square root of 4. So if you notice, yeah, those numbers are not the prettiest. If you'd like to make decimals for your square roots, you can. It makes it a little bit easier to graph. That's fine. If I move down to my next one, I've got a linear equation. These are values that are less than -2. And again, I'm going to use -2 as a boundary point. And all I'm doing is plotting points. Plugging in -2 gives me -11. Plugging in -3 is going to give me -13. Plugging in -4 is going to give me -15. Last one then is the constant function. Now anytime you have constant functions, that's like saying y equals 5. Well, y equals 5 is a horizontal line. So it doesn't really matter what I pick for my x values because every single y value is going to come out the exact same. It's all 5. That's the whole point to a constant function. So what I'm going to do is graph each one of these tables, and we're just going to connect the dots. So at 4, 1, I've got my first dot for my square root function. I'm going to skip over to 7, 2, because the other ones are going to be gradually growing with it, just kind of a guesstimation. And then as I move to the right, it's going to kind of bow out looking like that. Now we'll talk a little bit more in the next the next lesson about what an actual square root function looks like precisely, but that's just a rough sketch. The next set of points are my ones for my constants. Now notice that -2 is included with my constant function, but the value of 4 is not. So I'm going to come up to 5, 1, 2, 3, 4, 5, and I'm going to put an open circle at the point 4, 5. So that I would still pass vertical line test. Graphing the other points, if I come over to -2 and put my end dot, anytime we have a constant function, it's just a horizontal line, so that's all it's going to look like, is a horizontal bar. And then the last one is your blue function. Your blue function is going to go off the graph a little bit, so I'm just going to kind of fudge this and say that the bottom of this is going by 2's so that I can fit it all. So we're going to go -2, -11. So about here. And again, that dot is not included, so I need to make that open. So let me do that. So 2, 4, 6, 10. And then our next one would be at -3, -13. And then our next one would be at -4, -15. And that, again, is going to shoot off down, and you have your function. It's got 3 separate pieces. And if I drew a vertical line through the x value of 4, it would hit the purple but pass through the black. And if I drew a vertical line at -2, it would hit the black and pass through the blue. So my equations still make a function. If you have specific questions, make sure you write those down so that you can ask during class. And then also, please make sure that you add on the following homework assignment. You need to go to page 220, and you need to complete the graphs for 43 through 50. They all need to be done on graph paper, and please make sure that you have shown your XY tables for each one of the equations for all of the functions in the piecewise function. If you have questions, let me know.